Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about angular momentum, and we said angular momentum is simply the product of the object's moment of inertia and its angular speed around the same axis of rotation. That is first. And then we also talked about the law of conservation of angular momentum. We said that when the net external torque acting on an object is zero, then the angular momentum of the object remains constant, or it does not change. In other words, we can say the angular momentum will be conserved. And then we also said that the angular momentum is equal to moment of inertia times angular acceleration. Then we, of course, answered a few questions. We ended up right at this study tip. First of all, let me just remind you the equations that we've studied, and then after that I'll talk about this study tip that we have. We said angular momentum, it is represented by this equation, or this is the equation of angular momentum. L, it is equal to moment of inertia, that is multiplied by angular speed here. This is the angular momentum, don't forget. Angular what? Angular momentum, which is a vector quantity. This is the moment of inertia. Moment of inertia. And this one is the angular speed. Okay, so this is the equation of angular momentum, which is also a vector quantity. The direction of the angular momentum will always be the same as the direction of angular speed at this point. We also talked about the law of conservation of angular momentum. We said the initial angular momentum, it is going to be, or it is equal to the final angular momentum, that is if, remember, if the net torque acting on the object, it is equal to zero. If it is not zero, then the angular momentum will not be conserved. That is for one object, which in this case we can say moment of inertia, angular speed, moment of inertia, angular speed. These are, you can call them both initial, and these are final. You could just write initial for both here and then final for both. What if we have more than one object? Then instead of having one initial and final, we will have two. Let's say moment of inertia of object 1 plus moment of inertia. Why am I saying moment of inertia? Angular momentum of object 1 plus angular momentum of object 2. These are, we can say both initial will be equal to angular momentum of object 1 plus angular momentum of object 2, but these are both final, we can say. So this is the equation or the law of conservation of angular momentum for an object, or for two objects, let's say, when the net external torque acting on an object is equal to 0. And we said all the questions that we have, it asks for omega final, or what would be the final angular speed. We said if we have something like a merry-go here, it has a certain mass, it has a certain moment of inertia, it has a certain angular speed once it is rotating, so there will be a certain angular momentum at this point here. If an object is moving, it has a certain radius too. If an object is moving closer to the center, the axis of rotation, or away from the axis of rotation, then the final, or you can say the angular speed of the object, that is going to change, increase or decrease, depends on whether the object is getting closer to the center or moving away from the axis or the center of the object there. And this is the equation. Let me remind you the equation too. So most of all the questions that we have, it asks for omega final. So you could just write this equation and then it will answer all the questions here. We can say the moment of inertia of object number 1 plus moment of inertia of object number 2 here. These are, and then of course divided by moment of inertia of object 1, because this makes it easier to memorize, over a moment of inertia of object 2 here. So you can see both up and down at this point it is the same. Now we're going to separate or differentiate between the two. This is going to be initial, omega initial, and then this is going to be final. There's omega final here, but we just made the omega final here subject, so this is what we're going to write at this point. So this is the equation that you need to solve all the questions that we have in our book. So let me tell you regarding the study tips that we have here. At this point, don't forget, when we have an object, whether if it is a merry-go, a disc, or a rotating object, so whatever the shape is or the object is that is rotating, it has a certain, let's say, angular momentum, and of course you agree with me here. So that is one thing. If I want to rewrite the equation that I just wrote, omega final, we said moment of inertia of object 1, object 2 here is your initial, omega initial, moment of inertia of object 1 and object 2, this is going to be final at this point here. So, because this object is rotating here, so there are mainly two things here. One object that is rotating, and then there is another object, like a person, like an object that is being rotated here. So the object that is rotating is always bigger than the object that is on it. So you can call this one the main object here. So at this point, you can call this merry-go, all right? You can call this merry-go is the main object, okay? That is rotating here. And the person that is being rotated here, that'll be the secondary object in here. Secondary object, or the object that is being rotated here. Now, for this merry-go, whether it speeds up or slows down here, it has a certain angular moment, especially if there's no net torque acting on it. So whether it speeds up or slows down, the moment of inertia of the merry-go will never change. Why? Because it has a certain radius, and that's it. But for this person here, if it is moving closer to the axis of rotation or if it is moving away from the axis of rotation, then the moment of inertia for the person change, which as a result of that, it is going to affect the entire angular speed of the system, which is basically at this point, it is the merry-go and the person together. Now let me remind you, or perhaps give you an example of what this looks like here. Do you remember the ice skater? We said if the ice skater extend their arm and leg outward, the mass will be distributed far from the axis of rotation. In this case, the moment of inertia increases, the angular speed decreases, or the object rotates, or the person rotates slower. But what if it is the opposite? If the ice skater brings their arms and leg inward, closer to the axis of rotation, the moment of inertia gets smaller, because now it is the mass is closer to the axis of rotation. The moment of inertia gets less, angular speed becomes bigger. The object, it is going to rotate faster at this point. So this is exactly the same. If a person is moving away from the axis of rotation, now the mass will be far from the axis of rotation. If that is the case, we can say moment of inertia increases, angular speed of the whole thing, it is going to decrease. But if the person is getting closer to the axis of rotation, that is the same effect as the ice skater bringing their arms and leg inward here. If the person is moving closer to the axis of rotation, let's just erase this. If the person is moving closer to the axis of rotation, now the mass at this point, it is going to get closer to the axis of rotation. Moment of inertia will decrease, which makes the angular speed increase. So this merry-go, or the person with the person on it, it is going to rotate faster. This is exactly what we have. But so once again, the question will be asking about omega final, the final angular speed of the system, the merry-go with the person or the object will be on it, or whatever that is rotating, so you can simply find it. But in order to do this, first of all, you'll have to find the moment of inertia for both. For example, at this point, the merry-go and the person as well. But how do you find the moment of inertia for the merry-go, for example? For the merry-go, we can say, or you can rewrite it here at this point. Let's just say moment of inertia for the merry-go, it is equal to, it's like a disk, right? So it is going to be 1/2 mass times the radius in here. It has a certain mass, it has a certain radius. So neither the mass nor the radius of the merry-go doesn't change. So the merry-go has one moment of inertia. Even, it doesn't matter if it is rotating faster or slower, the moment of inertia for the merry-go, for the main thing here, it will always be the same at this point. Why? Because the radius of the merry-go doesn't change. Well, if the radius changes, that means the shape is deformed. In this case, nothing is conserved at this point. And of course, the problem or the example does not work any longer. So we can say, we have 2 points here. You can see moment of inertia of object 1 and 2. Now at this point, of course, you can separate them. You can, if we have a person and a merry-go, you can say this is for the merry-go. And then the other one, this would be for the merry-go too. And for the second one, we can say for the student here. And this is omega initial, which is going to be for both. Because if this merry-go is rotating, of course, the child would be on the merry-go. So the merry-go and the child will always have the same angular speed. Okay, so in this case, this two would have the same. Remember this two will always have the same moment of inertia, but for the student, of course, their moment of inertia, or the person, whatever the object is, if it is getting closer further, the moment of inertia for that thing or that object will change. Why? Because, for example, in this case, or this case here, our student here, if it is getting closer. First of all, moment of inertia for the student initial here, it is going to be, by the way, the student is considered as a point mass, because you can consider this, for example, just as a point mass that is rotating here. So we're going to use the equation of mass times radius squared. If you didn't know this one, you can look at the shape that this person, the student, this object is making while it is making and moving in a circle. That is the same as a ring here, and that is, of course, for the ring, we have mass times radius squared. So that's at this point here, the student has a certain mass and a certain radius, so there will be a certain moment of inertia. But if the student gets closer now, of course this radius is going to get less, right? So the moment of inertia will change. So we can say final moment of inertia for the student, once again mass times the radius, but this time the radius has changed, so the initial and final moment of inertia for the student or for the object will change. Perhaps I think it is time to solve a question, then maybe you'll understand even better than this. But remember, that is the only equation that you need at this point here. Okay, so once again, the main thing, the thing that does not, or the radius does not change, will always have one moment of inertia, both initial and final. But the thing that is moving or changing radius will always have two moment of inertia, as long as it is on the object. All right, so this is what this study tips is about. All right, so we have a question here. Says, what does it say? It says a 65 kilogram student. So how about we start with this one and first start with writing the information that is given here. All right, let's clean this. So what do we have? The first thing that we have says a 65 kilogram is, student kilogram is, or kilogram student is spinning on a merry-go-round. So here we have a merry-go, and there is a student on it. Okay, so the mass of the student, at this point I haven't read fully, so I don't know where the student is, but let me tell you something. Whenever you're given something like this, it is always recommended to make a table. I'll tell you what is the purpose of this table. Even if you don't make a table, it is pretty easy as well, but if you make a table at this point, it would be easier, and there is one reason why I would, perhaps maybe it will be more organized, let's just say. All right, so this would be, now at this point we have two things here. We have a merry-go and a student here. Which one? You could write the main thing first. Let's just say merry-go. Wow, I wrote M-A instead of E. Okay, merry-go. And a student as well. So of course each one of these has mass. We can say R1, radius 1, radius 2, and then there would be omega initial and omega final 2. So the first thing that we have, the mass of a student, it is 65 kilogram. And then merry-go-round has a mass of, what is the mass of a merry-go? 5.25 times 10 to the power 2. That is about 525 kilogram. Right, that's the same as kilogram. I don't have space. It says a radius of, so the radius of a merry-go is 2 meters. Okay, and then because the radius of the merry-go doesn't change, so here's the center of the merry-go. This is 2 meters. The radius doesn't change, so radius 1, both initial and final radius are the same thing, 2 meters, 2 meters. Then the next thing says, she walks, the student obviously, walks from the edge of the merry-go-round towards the center. So here she is, she walks from the edge of a merry-go towards the center. Well, Basha, if she's walking from the edge of a merry-go towards the center, what do you think her radius is at the beginning? Because the radius of the merry-go is 2 meters, so what do you think her first radius is? Isn't that 2 meters as well? Yes, so we can say the first radius for the student, it is 2 meters. Okay, towards the center. If the angular speed of the merry-go-round is initially 0.2 radian per second. So initial angular speed, it is 0.20 radian per second. The question says that is clearly for both of them. So you can write for both here. radian per second. And then the next thing says, what is the angular speed? So find omega final, which is unknown here, when the student reaches a point which is 0.5 from the center. So that is when she is at this point here, which is 0.5 meter from the center. That is going to be the second radius for the student. What would be the final angular speed? Now, since we wrote all this, of course, we can expand this one here, and then we can answer the question right away. So once again, remember what we had. We said, in order to find omega final, what do we use? We'll use one equation here. We said moment of inertia of object 1 plus moment of inertia of object 2, once again over moment of inertia of object 1 and object 2 here. These are initial, omega initial, and these are final, and that's it. So now I have two things. One of them is the merry-go and the other one is a student. Can I, instead of writing one, I'll just say merry-go here, merry-go, and this is for the student, and this is for the student. Now you can erase 1 and 2 if you want. If not, you can keep it as it is. All right, so what is the moment of inertia for the merry-go? By the way, we said initial because the radius of the merry-go doesn't change. So initial and final angular moment of inertia for the merry-go stays the same. These are both the same, and of course it has the shape of a disk, so the equation is going to be 1 over 2 mass times the radius squared. Once again, 1 over 2 times the mass of a merry-go is 525 kilogram times the radius was 2 meter, but don't forget to make it squared. That is 4. That would be 2 times 525. That is going to be 1050 kilogram meter squared. That is the moment of inertia for the merry-go. Now you can immediately write this into the equation. 1050, 1050. That's it. These are both initial and final. What is left now? What about omega initial? We have omega initial, which is 0.2. What is left now? Initial and final moment of inertia for the student. Let's find this one too here. For the student, moment of inertia initial for the student. Remember, the student, it is a point mass on a merry-go. So what equation do we use? We'll use 1 times mass times radius squared at this point. So we could just say mass times radius squared, which is equal to the mass of a student, this 65 times. The first radius for the student, we said it is 2, right? So 65 times 4, what is the answer equal to? Let's get this one, or calculate this one. 65. Was it 65? Yes. 65 times, let's just say 4, that is 260. What is it? 260, that is kilogram meter squared. So write it down here right away. 260. Now what is left? The final moment of inertia for the student. So the final moment of inertia for the student, it is equal to the same equation, right? Mass times radius squared. But because the radius is changed, so the moment of inertia will be different here. So once again, 65 times the new radius, which is 0.5 squared now. So 65 times 0.5 squared, the answer is going to be 16.25. 16.25. All you have to do that is the same unit, kilogram meter squared. All you have to do just write or plug this number into the equation. 16.25. And now all you have to do is just do the math. That's it. That's the whole thing. So I hope it is pretty easy. It's not that difficult with the monster, whatever that you're afraid of. If you just organize what is given and what is unknown, and you know what equation to use, then I guarantee you that is going to be very easy. But of course, you have to be very careful while you're reading the question, because I have a tricky question for you at the end of these questions. All right, so let's calculate this one here. Do each part at a time. So 1050. All right. Let me just double check with that one here. All right, very good. So 1050 plus 260 times 0.2, then that is 262. Of course, you can simplify if you want to. If not, you could write it down. If you're using a calculator, it's best to do each part at a time. Divided by 1050 again, plus 16.25, it is going to be 1066.25. All right, now do the math. It is, by the way, I forgot to mention this. Is the student getting closer to the center or away from the center? Clearly, it is getting closer to the center. So what do you think will happen to the rotational speed of the merry-go? Do you think omega initial will be bigger or smaller than omega final? Remember the ice skater. If the mass gets closer to the center, of course it is going to spin faster. Can I say the same thing here? Because the person is getting closer, the student getting closer to the center, so omega final must be larger than omega initial because the moment of inertia decreases, so angular speed must increase. So if you get a number that is less than 0.20, then your calculation or you've done something incorrect, double check your work again. All right, so let's do this one more time. That is 262 divided by 1066.25. The answer is going to be 0.2457, which by rounding I can say omega final, it is equal to 0 or 0.25 here. 245 or 246 doesn't matter, but by rounding I can say 0.25, that is radian per second. And that is obviously larger than omega initial because that was 0.2. And that is logically correct, calculation-wise is correct as well. And this is how you're supposed to do this one. All right, now let's go to another question and see if you can do that. But I would rather you pause the video for the next question, see if you can do that yourself at this point here. All right, so these are everything you need. And we have the study tip as well. It says the further an object from the axis of rotation, the greater the moment of inertia, which makes or slows the rotational speed. As a result, the final angular velocity decreases and vice versa. I think we've mentioned that one here. This question here, we have a bicycle wheel with a reflector. But at this point, like, it doesn't matter what the shape is or what the object is, as long as if the object is getting closer further, the moment of inertia change, which that of course it would affect the angular speed of the object. But remember this, in all the situations that we're using here, the angular momentum is conserved because there is no external torque acting, net external torque acting on the object at this point. So the second question that we have related to that or regarding that, it says a bicycle wheel. All right, so we have a 2 kilogram bicycle wheel. All right, so let's clean this one here. What do we have? It says there is a 2 kilogram bicycle wheel with a radius of this much. So there is a bicycle wheel. It has a certain radius. Here's a bicycle wheel. What is the mass of this bicycle wheel? Let's organize the information that is given. You can make a table or without table, doesn't matter at this point as long as you do this one correctly here. So we can say bicycle wheel, okay? And then there is a, what is the mass of a bicycle wheel? Remember, we have mass, radius 1, radius 2, we have initial omega and then final omega or angular speed, you could say. So the mass of the bicycle wheel, it is 2 kilogram, that is 2. Okay, it says with a radius of, so what is the radius of the bicycle wheel? It is 0.3 meter here. And of course, it is a bicycle wheel, the radius should not change because if it is changing, then you cannot use that wheel for the bicycle. So we can say both radius 1 and radius 2 for the bicycle wheel, that is going to be the same. That is one thing. Okay, it says turns at a constant angular speed of 25. So the angular speed, it is going to be 25 radian per second here. Okay, it says when a 0.3 kilogram reflector, so the next object that we have, it is a reflector. What is the mass of the reflector? It is 0.3 kilogram here. And then it says it is at a distance of 0.19 from the axle. So what is the radius? 0.19 meter from the axle. Then, what is the angular speed? So what is omega final? That is unknown here. When the reflector slides to a distance of 0.25. So the second radius, it is 0.25. But my question is the reflector getting closer to the center or away from the center? Obviously, because 0.25 is larger, so it is getting away from the center. So the question says, what is the final angular momentum? Okay, so let's do this one too. So once again, this is the bicycle wheel. So there is a reflector. What is the radius of a bicycle wheel? We said the radius, it is 0.3 meter here. There is a reflector at a certain distance here. And then this reflector, it is going to slide to a larger radius. So that'll be there. Okay, so the question says find the final angular speed. Write your equation. Equation says moment of inertia of object 1, object 2, over moment of inertia of object 1, object 2. We said this is initial, omega initial, and this is final, and that's it. And we said now we can name them here. You could say this is for the bicycle wheel, and this is, you can say, for the reflector, and that's it. You can call them number like 1 and 2. That is also totally fine here. So let's find the moment of inertia for the bicycle wheel. Since the radius doesn't change, so it has one moment of inertia, right? But what is the equation that we use for the bicycle wheel? Remember, if it is a bicycle wheel, it looks like a ring. So the equation of moment of inertia that you need to use, it is mass times radius squared here. So mass times radius squared. I don't write initial and final because these are both the same. So the mass of the wheel, it is 2 kilograms. The radius of the wheel is 0.3, and make sure you make it squared. So let's do this one here. That is 2 times 0.3 squared. It is equal to 0.18. That is kilogram meter squared. That is both initial and final moment of inertia for the bicycle wheel here. So you can write it down right away at this point here. So 0.18, this one 0.18 as well. And then what about omega initial? Let's write this one too. That is 25 radian per second. What is left now? Initial and final moment of inertia for the reflector. Watch this, because can I call the bicycle the main thing? Because the reflector is on the wheel, which is being rotated here. Okay, so the initial moment of inertia for the reflector here. Once again, the reflector is also a point mass that is being rotated here, so we'll use the same equation. Mass times radius squared. The mass is 0.3 kilogram. What is the initial radius? That is 0.19 squared. Okay, so 0.3 kilogram times 0.19 squared. The answer is going to be 0.01083 whatever. So let's just write it down. 0.0108. I'll write all the digits at this point. That is kilogram meter squared. That is the first moment of inertia, and you can write it here as well. 0.018. All right, 0.0108. All right, what about the final moment of inertia for the reflector? We'll use the same equation. Mass times radius squared. The mass is 0.3. The final radius is about 0.25 squared again here. So 0.3 times 0.25 squared, the answer is going to be 0.0187, and of course there is 5 as well if you want to do that too. So now all you have to do, just write this number too, 0.01875. Now all you have to do, just do the math, and that's it. So once again, let's do one step further. Add this to multiply by 25 and then divide by the sum of these two numbers. So let's do that. 0.18 plus 0.0108. All right. And then times 25. The answer is going to be 4.77 here. By the way, yes, and then divided by 0.18 plus 0.01875. We take another digit extra, so it's going to be 0.19875. We can say 88 by rounding. These are too many digits, by the way, but I'm trying to be as precise as possible at this point. Now, before getting the answer, should the omega final be smaller or larger than initial? Because the object is sliding, the reflector, it is moving away from the axis of rotation. So the moment of inertia of the whole thing, of let's say the whole bicycle wheel, it is increasing. So as a result of this, omega final must be less than omega initial. So if you get a number that is bigger than initial, then you have to recheck your work. Okay, so let's do this. 4.77 divided by 0.1988. The answer is going to be 23.99. All right, 23, which we can say about 24. So we can say omega final It is 23.99, which we can say 24 radian per second. And I believe that is perfectly fine because now final it is less than initial, which makes sense at this point. See how easy it could be, these questions? Once again, you only need this equation to write it down and then find the moment of inertia for each of the object that we have. Remember, the main object, the object with a single radius, or let's say that would be the main thing actually, would have one moment of inertia, both initial and final. That is the object that is being rotated. The shape does not change, does not deform, or the radius does not increase or decrease. But for the object that has the ability for the radius to change, it would have two moment of inertia. Find each, plug them into the equation, and then you can simply answer the question just fine. And that is how you could do that. Okay. So once again, there are some tips left for you, just so that you know once you go through them. The wheel has one moment of inertia because it has a fixed radius and mass, but the reflector has two moments of inertia because it is radius changes here. What is, perhaps maybe I didn't mention that, what is a reflector? Reflector is a piece of plastic you attach to the wheel of a bicycle, and during the night, once light shines on it, it glows light. I think we call it phosphoring Kurdish. Okay, so kind of like glows light in the dark. That is for safety though. Sometimes could be for decoration too. All right, so now we have another question which is also very interesting, and I'll tell you another question which is very similar to this one as well, and see if you could solve that one too. But before I solve this one, I would really recommend or love to see you pause the video, see if you could solve the question before I do, and then you can compare your work with my work, see how well you did. All right, and I'm sure you're gonna do well, even if it is your first try. Okay, so another question that we have is this one. What does it say? All right, let's bring this one back again. This one is a bit interesting because of one of the differences that we have compared to the other questions, the ones that we solved. What does it say? It says a solid vertical cylinder with a mass of this. So what do we have? We have a solid vertical cylinder, something like this. There is a solid vertical cylinder. All right, makes no difference at this point, I guess. So there is a vertical solid cylinder. Okay, so this is a solid cylinder, it's a vertical, it has a certain height as well. So let's make a table or write the information that we have or we're provided here. Just for the sake, just to make it more organized. So mass, radius 1, radius 2, we can say omega initial and omega final 2. Okay, I think this is too small. This would be for the solid cylinder. And then with the mass of, so what is the mass? It is 10 kilogram. I hope you can see this. All right, and the radius of, what is the radius? It is just 1 meter. Okay, so clearly the radius of the solid cylinder doesn't change. So the second radius is, you don't have to say the second radius, but just in case if you want to say that, it is going to be the same. And then after that, rotates with an angular speed of 7 radian per second. So what is the angular speed? It is 7 radian per second. Okay. The next thing says about a fixed vertical axis through the center. A 0.250 kilogram piece of putty is dropped vertically at a point 0.9 from this. So there is a putty here that was not on the cylinder while the cylinder was rotating here. Then this piece of putty dropped onto the cylinder at what distance? At a distance that is equal to 0.9 from the axis of rotation. Actually, I think we should make it at the edge of this because the whole radius is 1, wouldn't you? So 0.9 meter, that is how far it is from the axis of rotation. By the way, it was not on the cylinder first, but then it just got dropped on to the cylinder at this distance specifically. So we can say, by the way, so what is the mass of the putty? It is putty here, that is 0.250, and then once again, it was not on the cylinder here. So can I say the radius of the first one is 0 meter here? The second radius, it drops to a distance of 0.9 meter from the axis of rotation. All right, the question says, from the cylinder centers of rotation and sticks to the cylinder, determine the final angular speed. See, all the questions that we have, they're asking for final angular speed. So let's do this one too as well. 2. All right, so now once again, there is something you really have to be careful with this one, and that is this. Omega final, it is equal to, we said earlier, moment of inertia of object 1, of object 2, over moment of inertia of object 1, moment of inertia of object 2. These are initial, omega initial, right? I hope you memorized by now, and these are final. Now, because we have two objects, one of them I can call it cylinder here, cylinder and cylinder, and then this one you could call it for a putty, right? These are both, you can call them for putty and putty here as well. All right, and these are the rest of the thing. So what is the moment of inertia for the solid cylinder? Once again, what is the equation for moment of inertia for solid cylinder? It is like a disk, right? So it is going to be 1/2 times mass times the radius squared. But because the radius doesn't change, so both initial and final will be the same. That is 1/2. The mass is was 10 kilogram times 1 squared. So it is going to be 10 times 1, that is 10, which is divided by 2, that is going to be 5 kilogram meter squared. So now we can say initial and final moment of inertia for the solid cylinder, it is going to be 5 and 5. All right, what about omega initial? It is 7, right? So these are the numbers. Now, all you have to do is to find the initial and final moment of inertia for the putty. But here's one thing you have to be careful. What is the initial moment of inertia for the putty here? Was it initially on the cylinder? The answer is no. It just got dropped. The cylinder was rotating, and then after, let's say, a certain time, then this putty just got dropped into this. So, can I say the putty was not on the cylinder first? Yes. If it was not on the cylinder, what is the moment of inertia for the putty? It is 0. You could say mass times the radius, but if the radius is 0 because it's not on the object, so there is no moment of inertia for the putty at the beginning here. So we can say this part is 0, don't forget. Now what about the final moment of inertia for the putty? Now because it is on the cylinder at this point, so we can find that. And that is, once again, a putty is a point mass. If not, you can look at the shape of the path that it makes, that is a ring. So once again, mass times radius squared. The mass is what was the mass? 0.250 times the radius is 0.9 squared. And let's see, what is it equal to? So 0.250 times 0.9 squared, the answer is going to be 0.2025. What a number. 0.2025 kilogram meter squared. So now just write this one. 0.2025. All right, now all you have to do is just do the math and that's it. So it's going to be 5 times 7, that is obviously 35, divided by what? Divided by 5 plus, okay, 5 plus 0.2025, that is times, what am I doing? It just divide by the sum of these two numbers. And the answer is going to be 6.727, or you can say 728, or let's just say 6.73 actually. I think we don't have to do all this. That is going to be radian per second. Once again, should the omega final be larger or initial than omega final should be larger or smaller than initial? It has to be smaller. Why? Because this putty was not on the cylinder before. But now since there is an extra mass on it, and we know that mass is directly proportional with the moment of inertia, so if the mass increases, the moment of inertia increases. As a result of this, the angular speed must decrease. So let's compare these two numbers here. So this is omega final, which is 6.73. What was omega initial? It was 7. See? So now, of course, this number got lower. So logically, and math-wise, you could say, calculation-wise, these are both correct. Now, after you're done with this, of course, I have a question for you. And if you solve this question, I can guarantee you, or I can tell you that you are a very detailed person, and more likely, I can tell you that perhaps you might even be able, as a matter of fact, to get 100 as well. Not that this question, or not because, like this question is so difficult or whatever, no. Because this question has an idea in it, and that, of course, if you get it right, it just tells me how precise and how careful you are with the numbers. Let me hide the answers first. And of course, I trust you. If you saw the answer, you're not going to look at the answer. Okay, wow, man. Second time I forget to pin the whiteboard so that it doesn't go away. Okay, now, so which question was this? It is the this question right here. All right. I believe I cannot hide the whole thing. All right, I think that's fair enough. Okay, so here's what I want you to do. I want you to pause this video, give it a try yourself. It is exactly the same question that we just solved, but with a little bit of, change here. So I want you to pause the video, and also try not to take more than 3 minutes to solve this question, because if you take more than, actually just say 5 minutes, because that would be too much actually. So pause the video and solve this question, and then once you're done, just compare with the one that with the work that I'm going to do here at this point. And I hope you get it right. Once again, if you get this question right, not because it is too difficult, because it has something, an idea in it. If you get this one, I can perhaps guarantee that you're going to get 100, inshallah. Anyways, so let's say, assuming that you already solved the question, now you can resume the video, right? And you can check your work. It says what? A solid vertical cylinder. So we have the same vertical cylinder that you just saw here. That is this vertical cylinder. It's the same thing. Just make it a bit wider. All right, what does it say? It says with a mass of 10 kilograms. So let's make the table again. Even if you don't make the table, that doesn't change anything. We can say mass, radius 1, radius 2, and omega initial, omega final here as well. Okay, so what is the mass of the solid cylinder? There's a solid cylinder. The mass is 10 kilograms, the same as the one you just solved here. And then a radius of 1 meter. My bad, that's not what it is. So the radius is 1 meter. Because it is the solid cylinder, the radius is not going to change. So even final radius is also going to be 1 meter. I believe you did it this far correctly. And it rotates about a fixed vertical axis through its center with an angular speed of 7 radian per second. So here's omega initial, we can say it is 7 radian per second. These are for both here. Okay, the next thing says, a small piece of putty with a mass of 0.5 kilogram is on the cylinder initially at a distance of 0.9. So first, there is a putty on the cylinder this time. That would be one of the major differences here. So here's the axis of rotation for the cylinder, which is 1 meter. You can see that. So this is the radius here. There's the piece of putty here, initially at a distance of 0.9 meter. So there's nothing different about this one here. What was the mass? The mass is 0.5 kilogram. It is at a distance, initially at a distance of 0.9 meter here. Okay, so far so good. Nothing different about this. Then the second thing says, the putty then moved to a distance of 1.5, right? So the second radius is 1.5, that is going to be meter. And then from the center of the cylinder, determine the final angular speed of the cylinder. So I believe there's nothing much about this one. So let's just expand this one and solve this together. See if you fall for this or not. If you fell for this or not. So once again, omega final, that is what you're supposed to do, of course. Moment of inertia of object 1 plus moment of inertia of object 2 over moment of inertia of object 1, 2, these are initial, omega initial, and this is final, and that's it. There's nothing wrong with this one, right? And that's it. All right, so you can call this one cylinder if you want to. This one for the putty here. All right, so let's find the moment of inertia for the cylinder. That's perfectly fine. The cylinder radius is 1 over 2, mass times radius squared, and that's it. So 1 over 2 again. What is the mass? 10 kilogram. And then multiply by the radius, which is 1 squared here, which said is going to be 5. And since for the cylinder the radius doesn't change, so this is going to be 5 and 5. You agree with me up to this point, right? I hope yes. All right, and then the next thing is you have to find the moment of inertia for the putty, both initial and final. How about we write the initial angular speed as well? This is 7, all right, that is now moment of inertia for the putty, or initial for the putty. All right, so remember, putty is a point mass, so it is moving in a circle, makes a ring shape, you can say. That is, what equation are you going to use? Mass times radius squared. خلاص يعني. So what is the mass of the putty? It is 0.5 kilogram times the radius is 0.9 squared. So let's find the answer to this one here. 0.5 times 0.9 squared. The answer is going to be 0.405 here. That is going to be kilogram meter squared. Okay, so once again, kilogram. Wow, what am I writing here? It is 0.405. You agree with me, right? Now, what about for moment of inertia of, let's say, final moment of inertia for the putty? All right, final moment of inertia for the putty here, final. We're going to say, same equation, right? Mass times radius squared, yes or no? What is the mass, by the way? I think I'll have to move up a little, maybe. Let's keep an eye on this one here. So the mass is 0.3 kilogram times, what is the radius? 1.5. So what is the answer is going to be? Because the second radius is 1.5. So 0.3 kilogram times 1.5 squared, of course. That is going to be 0.675. 0.675, and that is going to be kilogram meter squared, right? And now you're going to add this number into, of course, you just plug the number in, 0.675, and then all you have to do is just do the math, right? I believe you got it right up to this point, yes? So you might say, so what is the trick if that is correct so far? Well, I would like to tell you, if you did it this way, you successfully did lose 2 marks in Wizadi. Hopefully not. But let me tell you this, Baba, you have, like this thing, because students always got into, like just plugging the numbers into the calculations. By the way, this is incorrect if you did it this way. I'll tell you what is incorrect. I'm about to. Because students just, like got used to in this one, whatever the radius or whatever the number they see or they'll get, they'll just put that number into the calculation, not paying enough attention to this, Baba. So what is the radius of the cylinder here? The radius is 1 meter, right? So the first radius for the putty, it is 0.5. That is totally fine. So here's where the putty is. That is at a distance of 0.9. But have you noticed what is the second radius of the putty? It says the putty is moved to a distance of 1.5 from the center of the cylinder. That is the trick. That is the point where you have to be really careful. And I hope you found this one yourself before I'm telling you this. Because if you move this putty to a distance that is 1.5 meter, isn't that out of the cylinder? Well, if it is out of the cylinder, is this putty like rotating anymore? No. So would it be the final moment of inertia for the putty? It is going to be 0 right away. That is the trick. I'll repeat this. The question tells you the putty is moved. It doesn't say slide, it doesn't say or whatever. It just says the putty is moved to a distance of 1.5. But don't forget the radius of the entire cylinder, it is just 1 meter. So if you move to a distance of 1.5, it is no longer on the cylinder here. And it is exactly the reverse of the question we just had, like the one prior to this or before this. The one before to this, it was initial moment of inertia was 0 because it was not on the cylinder anymore. This one here, the final is going to be 0 because it is not going to be on the cylinder anymore. So the final angular, for the final moment of inertia for the putty, it is going to be 0. Then, of course, you're going to get a correct answer. So at this point, because the radius is more than the radius of the cylinder, I did this work just so that, like just to I don't know, sorry for this, just to make you feel good for a second. Excuse me for that though. So, of course, because the radius is larger, so the moment of inertia for the putty, or the final moment of inertia, is going to be 0 kilogram meter squared at this point. So if that is the case, now you could do the math. It is going to be 5 plus this times 7 divided by just 5. I hope you understood this one, and I really hope you got this one correct as well. So it's going to be 5 plus 0.405 times 7, and then divided by 5 plus 0.405 times 7 divided by 5. So the answer is going to be 7.567. That is going to be radian per second. And of course, omega final must be larger than omega initial because the putty is no longer in the cylinder, so less moment of inertia, which is going to speed up in rotation. So that is 7.567. You can round it up to 7.6 radian per second if you want to. So let's see which one of the options is it's not an option actually, just like you have to solve this one or show your work at this point here. So once again, it says note that the final moment of inertia is 0. Moment of inertia, it is going to be 0 because it is moved to a distance that is bigger than the radius of the cylinder, which means that it is not on the cylinder anymore. So moment of inertia will be 0 right away. Okay, so what is the purpose of this question? But look, the purpose is you have to be very careful once you're reading the numbers. Like whenever you just see a number, don't plug that number into the equation right away. No, just first of all, give it a try. See if it makes sense. See if it matches the radius, the cylinder, whatever. Then once you're sure, then you can use this number in calculations. By the way, I brought that question to my students. Sadly, none of them knew actually, because it was totally different. And because perhaps it might have happened the same thing to you, because you just got used to this. Whenever you have a radius, you just plug that number into the equation of moment of inertia and then find the moment of inertia. But that, of course, might be different, or it might mislead you here. So let's take a look at these questions. And then perhaps we'll end the session for today. It says, which of the following equation represents angular momentum? You can see that is option A, angular momentum. It is equal to moment of inertia times angular speed here. The symbol L, what does it stand for? Stands for angular momentum. If an object, these are easy, I believe. By the way, not this one here. It says, if you take a look at this question 3, sometimes questions are very simple. It says, if the object's moment of inertia, I, it is 10, all right, and angular speed is 4 around the axis the angular momentum will equal to what? So sometimes questions are very simple. Angular momentum, it is equal to moment of inertia times angular speed. So you just have to multiply 10 by 4, and that is going to be 40. Which one is going to be in this case? Of course, it's going to be option A. Sometimes questions are very easy, so you don't have to overcomplicate questions for yourself. These are the same as the ones that we solved. This one too, it is also important. These kind of questions like this and that, been in Wizadi so many times, so you really need to know how you can solve them. It says that a skater rotates on an ice and the friction force between the two skates on the ice is negligible when he brings his hands closer to his body. Remember, this is the key word here. If they bring their hands closer to their body, what do you think will happen? Now, moment of inertia, of course, is going to decrease, angular speed is going to increase, but because the friction is negligible, so that means there is no net external torque, so the angular momentum stays conserved. So angular momentum, it says one of the following remains constant. What will remain constant? Of course, that is angular momentum. Angular speed is going to decrease because, angular speed is going to change because once they bring their hands close, moment of inertia decreases, so angular speed is going to increase. Of course, it is going to change here. it's not going to stay the same. Moment of inertia is also not staying the same because it decreases. Rotational kinetic energy, because if speed is going to change, so rotational kinetic energy, which is the next thing that we're going to study, will also change as well. During the rotation of a merry-go, watch out. This one is also important. It says during the rotation of a merry-go-round, if a child on a merry-go-round moves from, let's move this one a little bit, scroll it down. It says moves from a point near the axis of rotation to the outer edge. So goes from near the axis to the outer edge of the merry-go-round. The angular speed of the merry-go-round, like what will happen. So this is the merry-go. The person is going from closer, let's say close to the axis of rotation. It is going far from the axis of rotation, getting, let's say, away from the axis. We said if it is getting away from the axis, the mass will be far from the axis of rotation. So moment of inertia increases, angular speed will decrease at that point here. So let's see which one is it. It says the angular speed of the merry-go does not change. That is not true. It increases. That is not true. Decreases, yes. And says 50 kilogram. That has nothing to do with that because no number is given at this point. It says one of the following is the SI unit of angular momentum. And what is the SI unit of angular momentum? We said angular momentum is equal to moment of inertia times what? Times angular speed? Yes. Angular moment of inertia is equal to kilogram meter squared. And then for angular speed, it is radian per second, right? But the radian, let's just write it down. Radian per second, but because radian is dimensionless, so now you could ignore this one. So it is going to be what? Kilogram meter squared over second, kilogram meter squared over second, and that is option C. Okay, now question 8, also important, says when the ice skater brings his hand and feet closer to his body, once again, they'll bring their hands closer to his body, and then when the net external torque acting on him is 0, which of the following is true for his moment of inertia I, for his angular speed and angular momentum? We said when the hands are brought closer to the axis of rotation, it's too much, to the axis of rotation, moment of inertia is going to decrease, angular speed is going to increase, but because there's no friction or because the net torque is on the person is 0, so that means the angular momentum is going to stay conserved or constant at this point here. Okay, so which one of these options says this? Okay, it says moment of inertia decreases, that is true. Omega increases, L is constant, that is good. And then B says omega increases, that is incorrect. And then you don't have to follow the other one. This one says moment of inertia decreases, that is true. Up to this point, omega increases, but L increases, that is incorrect again, because if the net torque is 0, then L stays the same. Okay? If the net torque is 0, then L stays the same, which is incorrect here. So this one says moment of inertia increases, that is incorrect. So the only correct answer is option A. All right, I think there is one more question we're going to do, which is related to this. And then after that, we'll end the session for today. The next topic will be rotational kinetic energy, but this is one of the section review question. So we'll go to the question and then we'll come back for the rotational kinetic energy the next session. So this will be the last question for today. It says a student holds a 3 kilogram mass in each hand while sitting on a rotating stool. When his hand, let's say when his arms are extended horizontally, the masses are 1 meter far from the axis of rotation. All right, rotation, and he rotates. Let's just write what is given here. Okay, so once again, there is a student here. The student is sitting on a stool, sitting on a chair, you could say. And let's say he holds 2 masses here. Okay. He holds 2 masses at this point. Let's just make this one look a bit more realistic. These are not really, but okay. All right, so let's make the table again, perhaps. All right, so we have mass. We can say radius 1, radius 2, and then omega initial and omega final. Okay. What else? So holds a 3 kilogram mass in each hand. So we can say there is a mass, these masses here, there's 3 kilograms for each hand in here. While sitting on a rotating stool, when his arms are extended horizontally, the masses are 1 meter far from the x. So we can say this is the first radius. And as he rotated with an angular speed of, so what is the angular speed? It is 0.75 radian per second. If the student pulls the masses horizontally to a 0.3 meter, 0.3 meter from the axis of rotation, what is his new angular speed? So what is the final angular speed? Assume that the combined moment of inertia for both the student and the stool is 0.3 kilogram meter squared. Don't forget, this is not the mass of the student and the stool. No, these are the moment of inertia. So we can say for the student and the stool together, they have a combined moment of inertia. So you don't have to go by the mass, radius, and all that. They have a combined moment of inertia, which is 3 kilogram meter squared, and that's it. Okay, so how do you find the final angular speed at this point? Okay, so once again, we'll write our equation. Final angular speed, it is equal to moment of inertia of object 1, object 2, over moment of inertia of object 1 of object 2. These are initial, omega initial, and we can say this is final. Okay, so this tree here, we can say this is for the student on the stool. Student on the stool here. And these are, we can say, moment of inertia for both the masses here. This one is already given. This is 3 and 3 here. Okay, omega initial is 0.75. That is also given. All you have to do is just find moment of inertia of the masses for both initial and final. So let's do this one. The initial moment of inertia for the masses, because these masses are like a point mass. So once again, what equation are we going to use for them? It is mass times radius squared. If not, look at the path that they make here. That it is equal to 3 times the radius is just 1 squared. So in this case, of course, each mass is 3 kilograms, so 3 times 1. But don't forget, because we have 2 masses, instead of finding the moment of inertia twice for every mass, because we have 2 masses here, we're just going to use 2 times that. And the reason why I'm using this equation, because this is a point mass that is moving in a circle. If not, look at the shape that it makes once it is moving in a circle. So 2 times 3 times 1 squared, that is going to be 6 kilogram meter squared here. That is the initial moment of inertia. Now you can write it here. That is 6. Now the next thing is the final moment of inertia for the 2 masses here, which is again going to be 2 times, each mass is 3, but this radius now it is going to be 0.3 squared. That is going to be the second radius. So let's see what is this equal to. 2 times 3, that is 6. 6 times 0.3 squared, it is equal to 0.54 kilogram meter squared. Now all you have to do is just plug these numbers into the equation here. 0.54. Now 3 and 6, that is going to be 9. Okay, 9 times 0.75. It is equal to 6.75. We can do that. Okay, so let's do one more step. That is 6.75 divided by 3.54. 3.54. Just make this one nicer. 3.54, and see what is it equal to. 6.75 divided by 3.54. The answer is equal to 1.9 here. So we can say the final angular speed for the masses, the student, and the stool all together, it is equal to 1.9. That is going to be radian per second here. This is how you can do that, which I believe these are also pretty easy as well. Make sure that you read the question before you solve them. See what topic is it, see how you can, what equation do you need, and then of course you can start solving the question. That'll be the end of our session for today. Let's see what we're going to solve next time. Inshallah, we're going to start, or what what would be the lesson for next time. We're going to talk about rotational kinetic energy, and hopefully you'll stay with us till then. Make sure you practice a lot of Wazari questions, because now up to this point the questions are becoming too many. So if you don't constantly practice, you might get confused, and of course you might lost in the middle of the way. So make sure you keep practicing, and of course wait for more videos, inshallah. Till next time, take care of yourself. Assalamu alaikum wa rahmatullahi wa barakatuh.